Okay, so quantum mechanical model of the atom. So going back to quantum mechanics, you have the Heisenberg uncertainty principle where you cannot know both the position and momentum of an electron, but you can know the one or the other. You can't know both of them at the same time. And then here's the little equation. You have the uncertainty, and then the mass and velocity, and then you have Planck's constant. Really, I just threw this up here to show you guys. I'm not going to do any calculations with it or anything. So first thing is, what is an orbital? What we've been talking about, or what Bohr had shown us, is that we had this nice pathway that these things followed, but it doesn't follow that. You have to think of a three-dimensional, as in three-dimensional, and we know the probability of finding where an electron is going to be closest to the center of the atom. So if you were to look at a electron, some graphs of where electron probability, or graphs of electron probability, you can see here we have this gradient graph with, this would be our nucleus in the center, and then as you go out, you can see that our probability goes down. Okay, that gradient shows our probability. And you can kind of also see that into this other one over here. Again, it shows as we go out, the probability. We can see a lot here, us being able to find it in here, but as we get out to the outer edges, our probability decreases. Another, yes?
So does that mean that there's less electrons? Or that our chance of finding out where they are is less?
Your chance of finding out where they are is less. Like it'd be easier to find them closer they are to the nucleus than the further out they go. If you will look at this graph here down in the bottom left-hand corner, if we were to put the nucleus down here in this edge, and you can see that our probability versus the distance, as we get further from the nucleus, the probability of finding that electron, again, goes down. So you need to be able to look at all of these graphs and know what is going on. Where would be the highest probability to find an electron? Where is our lowest probability? This here is another way to look at it, with this hump being the 1s orbital. And then if we go down further, you would see another hump, and that would be our 2s orbital, and further and further.
So essentially, this graph is showing, these graphs are just showing the farther out you go, your probability of finding. It's essentially also just saying that there's fewer electrons, your probability increases.
Right. Well, I mean, the size is getting larger, and those electrons are jumping and stuff. So, okay. Any questions on that? That's about as far as I go with that. Now we're going to go to what you guys love, the periodic table of elements, breaking it down. So we have our levels and what we know of right now, and I'm going to denote that with N. We have 7 levels. 1, 2, 3, 4, 5, 6, and 7. If they should happen to discover a new element or make a new element later this year, that'll bring us to level 8. Okay. Some of the things, I'm going to ask you some math questions, or the AP might ask you some math questions, and they will be hypothetical. If you had an energy level of 27, how many electrons would you expect to be there? And I'm going to give you guys some equations to be able to work that out. So those are N's. Now,
What's
It says N.
In.
N. So then we have our sublevels. Okay, and our sublevels are our S, P, D, and F. So you need to be able to recognize that 1 and 2 are our S. And then don't forget that helium over here is an S. And then this big spot right in here is our D. These 6 over here is the P. And then down here at bottom is the F. Okay, so one thing I do need you to know, in the D, it starts at N. The levels start at N minus 1. So if I'm in level 4, when I go to D, I'm going to subtract 1 to get that level. So it's 3. So if you're in level 5, then you're going to go and N minus 1. So 5 minus 1 tells me I'm in 4D. When you go down to F, F is N minus 5. Or not 5, sorry. Jeez. N minus 2. So F is inserted in 6 and 7. So F really starts at 4 and 5. Any questions on that? Okay. So the next thing I want to talk about are s orbitals. So how many s orbitals are there in an energy level? How many sublevel? So how many would how many would level 1 have? How many s sublevels does level 1 have?
2.
How many sublevels? How many s's are there? 1. If you go to 2, how many are there? 1. If you go to 3, how many are there? S's. I only care about s's. Each level has 1 s sublevel, right? Yes. Okay. Each sublevel can have how many electrons? Each s sublevel. What's the most s can hold?
2.
If you go to P, how many p orbitals are there?
2.
How many p orbitals? There's not 6, there's not 2. 3. Each one can hold how many electrons? 2. 2 times 3 is?
Where are you?
So 1 and 3.
Where are all these numbers coming from?
P has 1, 2, 3, 4, 5, 6. But each one, so you have px, you have py, and you have pz orbitals. Because if you remember, if you go to S looks like this.
And then P has 3.
And then P looks like this. 1. There's 1. There's 2. There's 3. And then you keep on going.
I still don't understand what
So essentially, when you're in a p orbital, there are 3. They each set holds 2 electrons, and there's 3 sets. So we have a total of 6 electrons.
We look at, so we said P has 6. So D, there are 5 sublevels or rooms, whatever you call them. 5 rooms. Each room can hold 2 electrons, so it has a total of 10 electrons. And F has 7. Each one holds 2 for a total of 14.
Okay, so one more time. S has 1 orbital.
Yes.
2 electrons.
Yes. P has 3 orbitals with 6 electrons. All right. So what this means is if I'm looking at my equations I can tell you is that N is equal to our energy level. So if I look at energy level 1, how many orbitals are there? There's 1. There's only S, right? Okay. If I look at energy level 2, how many orbitals are there? 4. Yes. If I go to energy level 3, how many orbitals are there?
Do I count it?
I have an S, I have a P, and I have a D. 9?
And you have to be because it's N minus 1.
Yes, yes. If I go to level 4, how many orbitals are there in energy level 4? You have an S, you have 3 Ps, you have 5 Ds, and you have 7 Fs for a total of 16. So rather than doing that, if you just use your formula, if you say N squared will tell me the number of orbitals per energy level. So if I go to, say, energy level 5, so 5 squared would give me 25. And we only really talk about 1 through 4 because those are the ones that we have gone out to. We haven't gone out any further than that. Now, what if you have, they might hypothetically tell you, if you have the periodic table and it has 27 energy levels, then what's the number of orbitals in that energy level? And so 27 squared, all right? Now, the number of electrons, each orbital can hold how many electrons? 2. So if I take 2n squared, that tells me my number of electrons per energy level. So if they were to say you have energy level 27, and what's the maximum number of electrons in that energy level? You'll take 27 squared and then multiply it by 2. Okay. Any questions over that? All right. Sublevels and orbital types, they're the same. Okay, what's the maximum number of electrons in the 2s subshell? Maximum number of electrons in the 2s subshell. 2. What about the 3d subshell? 3d. The whole subshell, how many is the maximum electrons? Subshell, just in D. 3D, what's the maximum number of electrons in 3D? It could be 4D, it could be 5D. It's always going to be the same. 10. What is the maximum number of electrons in energy level 4? Energy level 4. And, we're going to do 2 times 4 squared. 32. What about, what's the maximum number of electrons in a 2p orbital?
6.
That would be the most common answer. It just says 2p orbital, not subshell. So since it's just one p orbital, there are 2. So you've got to look at those words. You've got to go back and understand that subshell is that whole D thing. If I just say an orbital, I'm just talking about one of those things. Okay? So 6 would be in a 2p x, 2p y, and 2p z. But I just care about one 2p orbital. It doesn't matter which one. Okay, so let's go to some of our rules. Hund's rule says that the lowest energy configuration is having the maximum number of unpaired electrons, so allowed by the Pauli exclusion principle. So if I were to take, say, the following, and I'm just doing something on like energy level 2, then Hund's rule says if I fill this one up, then all of these, I'm going to have the empty bus seat rule before I start filling each one up. Okay? Now, if it was filling the electrons and you were to see this, huh? Those are my arrows. If you were to see this and you saw that, is that a good electron configuration? And the answer is yes. Because this is X, this is Y, this is Z. That electron doesn't care if it's X, Y, or Z. It's not going to say I'm going to go to X first or Y first or Z first. It's going to go to just whichever one. Okay? So that is a viable electron configuration.
So each orbital has to be filled before
They start doubling up, yes. All right. So off-ball says that we're going to fill up the energy levels closest to the nucleus before we start filling up the other ones. So if I were to have, say, my 1s, 2s, 2p, we're going to fill up here before we start moving up. I'm going to make sure S is filled up before I start moving over to P. Okay, so we've got to fill each energy level up before we go on to the next.
Wait, how do you decide what to put in? Like, how many of those to put in the box?
The number of electrons. Each box is an orbital. Each orbital can hold 2 electrons.
So it doesn't matter which, it doesn't have to be like consecutive in like the boxes if you write this. Never mind. The 2p should have 6 boxes, right?
2p should have 3 boxes. This is a box.
Oh, yeah, 'cause
This is a box. This is a. Oh, sorry, I did go on further than I did. Sorry, I went to D.
So, Hund's rule applies to Ostwald's principle once you get into the orbitals with like more orbitals, subshells with more orbitals. Like once you get into P.
Hund's rule?
Yeah.
Yes.
Okay, so like the two work together. They're not.
Yes. Yes. Now,
technically, these are supposed to have a third arrow.
if I was doing oxygen, I was just doing something, but yeah, like that. Okay, so if I were to do this way, so if I had 1s, 2s, and then I had 2p, and we did oxygen, 1, 2, 3, 4, 5, 6, 7, 8. That is a violation of the Aufbau principle because we didn't fill up all of S before we went to P. Now, does this mean that this does not exist? No. What that means is that this is an excited state. So if you violate Hund's rule, or if you violate off-ball principle, it is an excited state. So they might say, here is your electron configuration for oxygen, 1s2, 2s1, 4 or 2p5. What type of state is that? That would be an excited state. Whereas versus the ground state, which does not break any rules. Questions on that? If you do not remember those rules, or you need to go back and study them. So now we're going to take a look at orbital diagrams. So an orbital diagram is where it shows our arrows and how we are occupying our orbitals. So if I have, say here, oxygen, dun, dun, dun. Why do I keep doing P as? So if I were to have that, then we're going to show how those electrons occupy this in a ground state. Again, if you see something that looks, say, if we were to have this, this. Again, it's wrong for a ground state, but it is it's an excited state because that electron from 2s went from 2s and it jumped up to 2p. And so now we have more energy, and we've gone to the excited state. Remember that your valence electrons are those last s and p orbitals. So if we were to have something like, if I were to do the electron configuration for vanadium, which would be 4s2, 3d3, my valence electrons would be that 4s2. So that is for vanadium. If I did vanadium with, say, a plus 2 charge, then that means it looks like that. It's lost the 4s2. The valence is your last s and last p orbitals.
What's the order of these? Like the S's and the P's and the E's and F's? Like, how do we know which one's last?
It would be like if I were to do this, if I were to do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Then my valence electrons is going to be my last s and then p orbital. So there's my last s. I don't have a p. So I only have 2 valence electrons in that one. If we would have went one step further and would have went to p, 4p, 5, that would be my valence electrons, and that is my valence electrons.
So S can go before P, but P can't go before S.
Right. S, then P. Yes.
So, to find this element on the periodic table, don't we essentially going to just pick down to 3D?
If you were to go to on the periodic table, I'm looking at what I am right now, you could count your number of your superscripts, and that total number should give you 35. Or you can go to 4p5 on the periodic table, and that should give you number 35, which is bromine. Okay, So let's go next. If you do not remember how to do the electron configuration, then here is that little map. Remember, we read the periodic table like a book from left to right. So we start at 1s and we fill it up. So 1, 2, then we start at 2s, 1, 2, then we go to 2p, through 6, 3s, and then 3p, and then we keep on going. And that is the way it goes. That's the energy levels. It's in the way of 4s has less energy than 3d. So now what we're going to do is we're going to write some of these. So S. What's the configuration for S? S is element number 16. So we are going to start at the very top of our book, 1s, 2. Next is 2s, 2. 2p6. 3s2. 3p4. S is 16. Make sure your superscripts match. We have 2 plus 2 is 4, plus the 6 is 10, plus 2 is 12, plus 4 is 16. Yes. Let's do barium. You ready? This is going to be a while. Huh? 16. The number of electrons, which is the number of the element.
So would the valence electrons be 6?
Yes. So valence electrons would be these right here. All right, so barium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Now, if I were to say, what is the core configuration? So we use core configuration rather than noble gas configuration. So when I say core configuration, what does the inner core of this look like? That's this whole part right here. So that would be the noble gas that comes before barium, which would be xenon. And then we're going to finish it out after that, 6s2.
I don't remember this now. Nobody has geography.
So in
You
this
said this
one,
was the what?
why aren't the
Core configuration, we'll also call it noble gas or shorthand.
5
So you just do
why isn't that counted?
the left.
That is the valence electrons on this one. The valence electrons in here would be where? Where are the valence electrons here? Here and here. Yes.
What happens if it is?
If it's a noble gas, if I ask you what's the noble gas configuration of xenon, then I'm going to go to the gas before xenon, which is krypton. I'm going to say krypton, 5s2, or what is it? Yes, 5s2, 4d10, 5p6. You cannot be your own noble gas configuration. So you cannot tell me that this is xenon.
What was the other name of this? Because it wasn't
Noble gas or a core, because that core is that whole thing. Oh, wait, barium. I'm wrong. It is 6s2. Sorry, I was wrong. Right here.
So it's your last S and last P.
S, then P. So that means this is just showing my valence electrons. When you do the core configuration, it should just show your valence electrons.
So for xenon, the valence electrons, they would have 8.
Yes, for xenon, the valence electrons would be this and this. All right. So let's go to the next thing that says, write the electron configurations for magnesium, krypton, RH, platinum, and bismuth. Show both the full configuration and the core configuration. So I'm not going to do that. I'm just going to pick one of these and do one of them. So you guys want to do one of the transition metals?
Yeah.
Okay. So let's look at platinum. All right, so platinum is number 78. So if we do full, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Geez, I could have picked a smaller one. 4d10, 5p6, 6s2, 5d, 1, 2, 3, 4, 5. Oh, see, now you guys, it's not.
Is it 7?
No.
Would it be
What comes after 6s is 4f. So it would be 4f, 14, and then we have 5d, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7.
D1 and then
5d7.
4F?
No. Okay, so when you're looking at your, let me pause this.
So the valence electrons would just be 6s2, so 2.
So your valence electrons would be, yes, this one right here. Your highest energy level, which one? Highest energy level is 6. Highest energy electrons are located right there. Your highest energy electrons are your last ones. All right, so let's just take this all out and go to our core configuration. So our core configuration would be xenon. And then we go to 6s2, 4f14, 5d8. One of the things too is if you it doesn't look right, go back and count those superscripts and make sure it adds up to 78. All right, so moving on. Go practice those. So what I want to talk about is paramagnetic versus diamagnetic. So the very first thing says, using the element silicon, show an orbital diagram. So I'm going to do silicon. So we have 1s, 2s, 2p.
Do we have these boxes?
No, you can do whatever you want. 3s and 3p. And we need 14 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So using this as our example, it wants to know if it's paramagnetic or diamagnetic. So that is talking about the electrons. So paramagnetic means we have one or more lone electrons. Diamagnetic means that all of our electrons are paired. So we're paramagnetic.
Why is it called paramagnetic?
I think it has to do with the spins
Oh.
of the electrons. So now we are going to talk about chromium and copper. So this is for the chromium family. This is for the copper family. Anybody below chromium? Anybody below copper? Remember, chromium is a D4. Copper and its family ends in D9. So I'm going to draw two things. I'm going to draw the expected, what we expect it to do, and what it actually does. And we're going to do this for both of them. So chromium, it is, if I take a look, I'm just going to draw the last energy level of electrons. So I'm going to draw 4s and 3d. 1, 2, 3. Okay. So if we were to draw these, I need to have a total of 4, 5, 6 electrons here. So what we expect is we would have 1, 2, 3, 4, 5, 6.
Why is there 5 boxes?
D always gets 10 electrons, which is 5 boxes. Now what actually happens, and you will have a question on this on your test, is that the D and the S orbital are really about the same amount of energy. And so for the chromium families and the copper families, their excited or their ground state looks like this. We have our electron there. And then we want to fill up every room in the 3D subshell.
And this is because
The electrons, they don't want to be with each other, right? So if the 4s has 2 in it, but there's an empty room over in 3D, I'm going to jump to 3D and be in that empty room so I can get away from that other electron.
they're like siblings.
They're like siblings, yes.
But it's still similar.
But so it's still the same number of electrons. Now, chromium has a 4s2 3d. 4 is what we expected, but we all actually do 4s1 3d5. So that is its ground state. This is for everybody in chromium's family, anybody below chromium, so chromium, molybdenum, tungsten, and then everybody below copper. Yes, so if I look at copper here, I have 4s and I have 3d. Then we have 1, 2, 3, 4, 5, 6. So we have 4s2, 3d9. But, again, oh, dang, no. All right, there we go. So what happens is this electron in 4s jumps over to make 3d be fully filled out. And this is our copper configuration and copper family configuration. So it is a 4s1 3d10. Because it's better to have that one little sublevel alone than that one that's in that has 5 sublevels in there.
Like silver and gold.
So silver and gold, yes. Copper, silver, gold. Questions? So I'm going to stop there. Tomorrow we'll pick up after the quiz the core configurations for those other things. And then tomorrow you'll have time after that to work on your homework.